What I would like to do is, I also have a presentation to give you discussing about the overlay, right? But I would like to wrap it up a little bit so that we will take you through some of the examples that I have for the class, covering from the beginning when we start a very, very simple assignment, okay, and then going through the sim dicing, going through the DIM8, how do we do the DIM8, how do we do the DIM8 list, and we were discussing about if we have a large array of data, okay, in the main memories, and how do we DIM8 that memory down to the local store, so our local store program can run that one, and through which techniques, the DIM8 list, the multi-bufferings, and also the discussion of after we exceeding 256 byte or 200 byte, who is going to take care of that one? Don't forget, all of the operations and DIM8 was handled by the MFC. The MFC will handle that once we do the MFC list commands, the MFC hardware will handle the supplying using the data and the address from that list. We will supply the data to your programs. I will show you how to do that one. Okay, let's say that I will take you a tour here, right? And bear with me, that's some of the things that we may seen before and may not, right? Let's say that we have a very straightforward program, right? We all understand this code. We have a float of ABC, right? And then we have a main program, so we do A equal to B plus C, and then we return 0, okay? And now we'll take you through and ask you to show me how to convert these programs to SPU programs or the PPU or whatever, the embedded program we talked about the last 2 days, right? Today, if you have any question, Hema and I will respond to you and answer your question, right? So we'll quit over here. All right, so now what we need to do, this is any program. What we need to do in order to make this one is a PPU program. Just compile ASA. We do this. What compiler that we use? XLC, GCC, SPU minus GCC, right? T2.C, correct? If we want to put down T1.C, fine, that's good, right? Oh, okay. I have a T.C and T1.C. We'll show you what it. All right, so we're okay, right? Do a list. We have something A.out. Can we execute this program now? No, not yet, right? We have to bring it over simulator. Fine, we don't worry about that. Okay, now let's go that. Let's make this program, practice program as a PPU and SPU program. Okay? And tell me how to do this one, all right? So let me have this one program, bring it back, T1.C. Okay, what portion do we want to make an SPU and what we want to make a PPU? Okay, let's do this one. Okay, let's say that this one over here, we will make it as is what we save these programs. We will make this loop here, these operations as a SPU program. Okay, so we save this one, write this one as is T1 underscore PPU dot C, and then we figure it out, right? And then we write a lazy one, right one is a T1 underscore SPU dot C. So we save sometimes. Okay, right? So now we go back in here. We say that we have an SPU program. This is our SPU program. And now remember, float A and B and C. We just bring it down there, right? So we have an applications, an SPU application with its own data, right? We keep the data down in the SPU. Okay, it's fine. Okay, main here, the same thing. Insert arguments. This is an SPU program, right? 3 arguments that we need to have. Number 1 is, all right, unsigned long, right? Unsigned, long, SPE, what? ID, right? We need to have an SPE ID because this is an SPU program. Unsigned, long again, of what? Argument pointer, ARG, right? and unsigned, long, environment pointer, env, p, whatever, right? Okay. And, okay, so we have this, we have a ABC. Do we need to do anything here? The data is still here. I bring the data to float ABC down to here. Okay, so we finish, right? Hema, make sure that I do the correct programming here, right? All right, so we write and quit. Okay, VI thì our PPU T1 underscore PPU dot C, correct? All right. Now I have the data down in my SPU, so I just go ahead and delete these guys, right? Okay, delete these guys. Okay, this loop or this operation here is now belong to the SPU. So I comment this out, right? I insert this one, comment this one out, and I return this. I need to return this one. All right. So this is my SPU PPU code. First thing, what I need to do? I need to create an SPE thread, right? SPE create thread, correct? Right? And I give what? What is thread? TAD. Hammer. Wait. All right, thread. All right. And then what? The first argument is what? My group ID, right? I put it 0. So this is my what? My group ID. Group SPE group ID, right? SPE group ID. Okay. The next one would be what? What's the next argument here? My program handler, right? This is the pointer to my program handler, which is T1 underscore SPU, right? Comma, this is my program handler. Okay, and go down. The third argument is what? My pointer, right? Which is my node now over here. I just put node here because I will say that, all right, this one is my argument pointer, pointer here, and then the third one is node. Okay, and then this is environment pointer, envp and envp pointer, right? And then I have and then what they have? We have a mask ID, right? Okay, the -1 when we use -1 because it's not working fine, you know, as of now. Okay, this is my SPE affinity, right? T. And then we have a 0 with a flux, right? That's for the TLD, right? Okay. Flux, right? The flux one for my. Okay, and then what? Then I have to wait for, right? I always have SPE wait. Okay, SPE wait for my SPE ID right? SPE ID status and 0. Now we're going back up, right? This code, right? We return what? Voila, yes. In SPE ID return to, right? SPE ID, not too fast, right? Now SPE ID, so we have this one, so we have to declare the SPE ID somewhere, correct? And okay, SPE ID underscore T, right? SPE ID underscore T, what? It's my SPE ID, right? Status, I declared over here as well, so I have to int status, right? Okay, now in this program I use what? T1 underscore SPU, which is my program. I have to go back up here. I have to declare some things up here, right? Before reach to main. Right. Extern what? Extern of SPE underscore program handler underscore T, right? And then the name of the program is T1 underscore SPU. Right? That's it. So that's my SPE program. Correct? Alright, what a quit, right? And my make file. My SPU make file. What look like my SPU make file? VI, let's for example, right? This because I would have the directory. Okay, so now we have the PPU program, the SPU program, correct? We need to do the Makefile. The Makefile is on the PPU, straightforward, right? We specified what? Okay, let's do it. This is the Makefile for the PPU, okay? I'm just make it up so that we go. This is the, well, this is already made. This is the Makefile for the SPU, right? We don't have anything here. And okay, let's say that, let's assume that this one is the Makefile for the PPU, right? Program underscore PPU here, right? And the T1 PPU, correct? And then what? We have to import, very good. Import ORTS, import what? Import the, we assume that T1 underscore SPU dot A, the files right there. Okay, and then the last one. Now let's say that this, if this one is an SPU Makefile, okay? This is SPU Makefile. Okay, so the program is the SPU, correct? All right, and then over here we do what? We say that we do the library, right? We specified a library embedded. All right, library underscore embed equal to what? What we embed in here? We embed under, let's say that this is the SPU program under the SPU directory, correct? Right? And we embed, so we have to go back to the PPU program, add the directory dir equal to SPU, so we do the SPU. Blah. Details, you know. Okay, SPU T1 underscore SPU dot A, right? And then LSPE, correct? Okay, so we have in here. What I have shown you is that a typical, this on the PPU programs, one thing's missing. What do I miss here? Included. But include what? Include what? Live SPE.h, right? This is unneeded because I do the thread creations. If I don't do anything, you know, I don't need this, guys, right? Okay, so, all right, so we have the T1.c program. Fine. So far, so good? All right, let's take a look at T.c program. Same program, right? Now we float, we make an array, 3 arrays, 1,000, 1,000, 1,000. And the main is, you know, now we do a loop, we do from the loop count and we do loop, right? So far we okay? All right, okay, let me go back to here, and then the day 3 sim trees. And I will go to what I have in here, and I'll show you. What I have in here is have a directory of 7 different test cases, right? I have the one PPU only, one is self-DMA with one SPU. We do the transferring here, okay? And then we do another DMA transfer example here, and we do the DMA list transfer. We do the multi-SPU. We split the task into different SPU. And we do the multi-bufferings, and we do the software cache. The software cache I mentioned yesterday, but I did not have the time to go through. Forgive me because that I want to bring you up to speed so that we wrap it up, remind you what we've been through, and now let's take some real examples. And this example here, this is the H file. Okay, use the text file because this is quicker than go do this. And this H file, what do we have in here? This is an open source version, so it's all come help. I don't have anything. Okay, so I'm going to bring it up. This is my PPU programs. Okay, bear with me. I walk through a little bit slowly here, but then I move it on kind of fast, right? Standard IOH, we don't, is it clear enough for all of you at the back? It's okay. So what we have in here, we define an array size of 1024 and a number 512. And I use this one so I can define the alignment of array A, array B, and array C. Okay, it's a little bit changing, but here nothing else. We say that my align here, given my var, def defined, and my array, my alignments here, and then we define the attribute would be for this one. So I use this one here to define the my align of array A, array B, array C. It's nothing else but to define array A is an array of 1024, alignment of 128 byte, align of 1028 byte, align 128 byte. So what I'm going to do here is that I'm going to add the two elements together, all right, and put in C or in A or B, whatever. Okay, so this is a routine I use to initialize an array, nothing else, right? I put an array here, I call it init array, and I have an array 8 sub I here. Go to all the I elements, I times num times 2, and so on. Clear? So far we okay? Nothing, no, we haven't done anything yet. Let's look at the main program here. There's some tricks, some techniques that I would like to share with you. That's up to you to use it or not, okay? In here, we do the integer array, right? We do an add array. Array C, A plus B. That's it. Instead of two numbers now, I have an array. Okay, C equal to A plus B. And I print out the array, verifying some number. That's my PPU program. So far, you with me? Okay.
This is standard program, not a PPU program.
PPU program, standard, right? We haven't called anything. We haven't split it yet.
Okay, we haven't split it.
Right, okay. All right, you will see. Okay, so we have that. And then PPU only programs. That's the only thing we have. Let's take a look at these guys. All right, in the step 1, array of H. Okay. What I'm doing here is that I define a structure here. I call it control block, right? I have in A, I have A, B, and C. Okay? And I also have size. So each of the elements here is what? 4 byte, 4 byte, 4 byte, 4 byte. Okay? I will align the control, this structure here to 128 bytes. So I have to pass it here, right? I have to pass that address, so I have 128 bytes. Okay, so that is my control blocks. All right, we finish that one. We take a look at the step 1. Step 1 corresponding to the programs that has not SIMDICE yet, and step 2 is the SIMDICE version of the program. Okay, so you have a Scala version and the SIMDICE version, what you can look at, when you get the times. This afternoon, or if not, I give you this one. You can look at, by the times you go home and so on. Let's look at the SPU program. All right. I bring up this one using my text path. Okay, this is my all right, I will get out this one. I would like to bring up the SPU program as well, right? So I can put side by side and we go over, so what's going on? Right, so I did that, and then on the window, I put them, I tie them vertically, right? Okay, so this is what? This is my SP program. Okay. What I'm going to do is that in this program here, this is my my PPU program. On my left side is my PPU program, the right side is the SPU program. Correct? All right, so on my PPU program, I'm go ahead and allocate it, define it, the alignment of my array here, A, B, C, correct? And then initialize it here. Didn't change anything? Nothing. Okay. Then I initialize the main program, initialize the array, and we create an SB thread. Okay. and create an SPE thread to process the array SPU. Okay, I create an SPU here, an array, create the threads, and in this example, I will send the address down to the mailbox, which I really don't want to show you yet, but just go ahead and show you here. I will send effective address to the SPE down to the mailbox. Okay, I create an SPE thread, and this is my SPU program. Nothing, I send it out, right? I will use the mailbox to send an address down. The mailbox is used for message, sending message, all right? In this case, instead of sending message, I will sending an address down. I will use the SPE ID here, which the SPE ID that I just created, okay? And I send the address of the array A and put in that mailbox. This is the address of what? Of the array A. And this is the address of array B. Okay? And also this is the address of array C. Why do I want to do that? Why do I want to do I can either send my address down when I create the thread. I have 3 arrays, so I have to do the same thing for 3 times, right? Or I can send the address of the control blocks, and that the control block contains the address of my array A and B and C. Or I can do this one as well. That's why I want to show you the 2 different techniques. This is the first technique, using the mailbox to send it out to an address of an array. All right. So we do that one. We have the address. By the end of this one, I send it down to the SPE 3 address of the array.
What does that function SPE stat in the mailbox do?
Okay, so now on the SPU programs, on the I have the control blocks declared here. There's my local. Okay, somewhere. Okay, right here, the alignment control block. This control block is local. CB is local to my SPU programs. I still declare the array A and B and C right here. I get the control with the argument pointer from these programs. I get the address, the effective address from the ARPGP here. And then the size of the control blocks, okay, and the tag here 31. So I get that I get that address I get the address of the control block down. So by using now the MFC get, where I have the address of the A here and B on the local now, and the components is the A component, the address of the array A and address of the array B here. I download it down to my local areas here, and then perform the calculations. I perform the calculations just right here. Okay, same things. A, B, C, C equal to A plus B, whatever. When finished, I send it back. MFC put here, array.c, array_c is the local array. The effective address is CB in my control blocks. And then the size and so on, I send it back. So what we did was that what we had before was that we have in the addition operations on the PPU, right? And now we shift it out to the SPU, right? So everything that now, instead of having the data down into the SPU, we said we keep the data somewhere in the effective address, right? And when we send a control block down, so we can identify or we can acquire the address of the array A and B and C, and then we use that one, demate the data down. Okay. Control block techniques, right? No mailbox, nothing. We have a control block we defined before on the array underscore h underscore add.h here, that heading file. We declare the array here, the size, one array size alignment 128 bit, 128 byte alignments. We have a function here to do the initialize array in a main program. Look at the main program. We initialize an array, okay, and then we check the number of SPE working. You know, this is an extra news. If you want to be really careful, you do that. Only it's the same, right? And now, here it is. I think it's much better. It's much clearer for you. This is the CB.A. This is CB.B and CD.C. The C of we get the address of array A, beginning the first locations, right? And we give it to A, CB.A, refer to CB.A, and we get the address of array B, okay, and send it. This is B components, okay, and address of C, and then the size, and C size, okay. We clear this structure here, and then we create an SPE thread. Again, the same thing, group ID, the name of the program, and here's what we send it out. We send a control block down. Okay, so what we send a structure down which contains address of A, address of B, address of C, and each of these guys is 1,000. Do we care about breaking up? How? We don't care yet, right? And so we go into print. After that, we print and so on. We don't care this one. And here we synchronizing, right? A lot of time we talked about, you know, how do we know, and when do we know that we finish transferring the data, and how we sync the address between the local store and effective address. This is the typical instruction we use to sync between the two of them. Okay, we do that one and we wait for the SPE complete. Okay, so this is the SPU program. On the SPU programs, I define everything the same like we before. This array here, control blocks. This is my local control block CB over here. And then the first one would be, you know, to get the, I already have the control block passing down for me in this argument here, right? So I go ahead and use that argument and get the data of the size of the control blocks. Bring it down, and then now I have the control block down on my SPU. Oh, now, all right, so I use that one now. I refer to the components A, use that one to refer to my effective address, and use the CB, and then do the two MFC get, right? One to get the A, one to get the B, and then write tag mask and so on. And the size already specified by the size that I have when I bring it out into argument pointer here, passing to me when I create a thread. I do the matrix add, and I put it back. I put the box C here, CBC. So what we did was that we have a control block down, you know, somewhere, defined that containing some address of an array A and B and C and the size and so on, and we pass on the PPU. We use that one to load the data, and then on the SPU we pass that control block, the address of that control block down to the SPU, so we can refer to the element within that control blocks. That's it, all right? And then we use that one as an effective address, so we can download, you know, the data to array A, data to array B, so we can perform this operation here. And we use the same strategy again, send it back to the PPU program. That's how do we break up the data, and then how do we change. This is the SPU versions of the programs of the SPU program we just mentioned about. And however, this is the vector versions, right? And here I do the same things. My define, my alignment is still the same. And my arrays, I declare the array now instead of the full array size, 1024 or something like that, I divide it by 4, right? Because now I declare this one is a vector. My array A contains a vector. It's a vector of elements. It's a vector of array B and a vector of array C. Control block the same. Okay, I do the same things. I form, this is a SPU program. I get the control blocks from my argument list over here. Check the tag mask, status, whatever. I get the array. We do the same thing, do the same thing, do the same things. Nothing changed in terms of data transferring. Get and put do the same thing, right? Through the control block. Okay. The actual operations Now instead of array of sub I equal to array A plus array B, okay, we have a SPU add. I have to use intrinsic functions to add these guys.
And you have got 4 statements just to make sure that the loop instructions are less.
We get 4 statements over here because of what? Because of what we're doing here. Unroll the loop. We unroll the loops right here, right? So we not only vectorize this one, but unroll to make some optimization as well. So that when we speed up, you can leave it here. If arrays 4, whatever, just doing one at a time, you know. But
Tracing the patterns.
pardon me?
Tracing in 4 parts.
Right.
By just converting, because are we operating on vectors? Because
Yeah, we'll.
instead of scalars, we are operating on vector flow. Right. So we are operating on 4 bytes per line instead of 1.
4 elements, right? Yeah. The story here is that once you, the vectorized versions is, you have to take care of your data here. It's now instead of single elements, it's now 4 elements per instructions or per array, and then you do have the calculation that you need to take care of. Memory transfer remains the same, nothing changed. So you deal with data only.
Possible to get a single variable out of a vector?
Single element extract, right?
Expector.
Right. Okay, so we finished that one. Let's take a look at the DMA list. Okay, this is the array H, I think will be the same. I didn't change anything. The control block. Okay, this control block remains the same, right? And now we add the structure here. Remember this, the element of the list is an 8 byte, all right? And then we have the first bit, whatever. We have the store bit, and then we have some of the bit reserved here, and the number of bytes transferred is 16. So this determines the bits structures here, and then the size of this one is the unions of this unsigned int on 32, and then this structure here. So we define this one is the unsigned int elo. All right. Step 1 on my PPU program. What I'm doing in my PPU program. In my PPU program, I still floating, declare my array here. My control blocks the same. My control blocks now contains A, B, C, the array, and then the size and so on. So I have this one the same, nothing changed. I'm go down here. I check for the working hardware, nothing changed here. My control blocks get the data from my control block. I said A and B and C. And I create a thread. Okay. The SPU program, we pass the control block down, and we wait for SP finish. Do we change anything? Nothing. Right. Okay. So far so good. We just go over here, and we pick up the SPU program. No, wrong one. Right here, right in my list. This is my SPU program. My array is the same, nothing changed here. My DMA list now, I have this struct. We call the DMA list elements. We call that list. We have 16 elements. So 16 mean what? We have 16 command, right? A list of 16 DMA commands. Okay. Why the 16 DMA commands? Because how many bytes we transfer out every time? Maximum is what? 2K? We will see, right? Okay. Align 8 byte, right? DMA have control blocks into local store. We get that DMA control blocks. So we have everything down to the local store now. Next, we do have what we call the transfer to large regions. Okay, And now we have two routines here, right? We have one is transfer to large region where we go ahead. We call this routine here, transfer large regions. We give an address of an array A. We say that, okay, now transfer the address of the, go ahead and get this effective address here that I passing in my control blocks, okay, and locals is the array 8 over here, and this is the size, how many that you translate going down, and one I think that's the sum the flux I set down here. Okay, this is my transfer to large region. Let me go through here. There's been a couple of weeks I work in this one. So inside tag ID, the list size. If the number of bytes not equal to 0, whatever, we return. Okay, greater than 0 inside the size over here. What I'm trying to do, the same thing like the Hema just explained. I'm walking through the list, okay, and I say that I have if I answer the size, if I have it greater than 16K, right? The size over here is n byte is less than 16, 384. Or n bytes, or otherwise n byte is 16K. So I move 16K at a time. And then down over here, list of I, the size 032, I put the size in there, and then my effective address load, I put in here. And then increase the size, I reduce the size of the buffer, of my main buffer there, of the arrays that I have, and then increase that size, how many more bytes that I transfer. And I go back to this loop. So what I'm trying to do in here is that I transfer 16K at a time, and I use the EA low to identify to move my pointers right the next. I move this one, 16K, and then next 16K, next 16K. Okay? And then the list size here, we take up the size of the DMA list elements. Okay, so I have that. Now, I have all these laid out for me, and now I do the actual work, right? Now, if I pass to either 1 or 0 here, right? If it's 1, if it's get here, I define a get somewhere, it's either 1 or 0, and this, depending on the condition that the flux I set there, I can do the get list, put list, right? If the get list, I have the local address right here, and the list elements start by the first elements, and give it the effective address load over here, and then the size, the list size, and the name of the list. They are the first location of the domain list, and either put out, and this is correspond to the same exactly. You see that all of these instructions, MFC get, MFC put out, basically the argument list is the same argument list. Right? So either we specified the local stored address, the effective address here, and then the list address. Right? So then we let it go. Do we care about how often and when we finish or not? No. Right? We just use this subroutine here, okay, to get the data and supply it right here. We move, this is how we move the data to array A, move the data to array B, and then so we perform this function here, and then we transfer it back. And we use this flag here to say that this is my put L. So we use the put L, the get L, and the put L to get the data is in a list. So we don't have to worry about just individually. So that's a different techniques we use.
We have seen both the examples doing exactly the same thing.
Correct.
Okay. So even in this list example, since you are putting it into already defined arrays, you are not exceeding 256K at all.
Okay.
Okay. So the question of 16K into 2K doesn't arise because you will never exceed that. You are putting it into this particular array.
All right.
So what is the advantage of a get list over a single call which gets me the full array?
The point is in one DMA transfer you can use 60K byte only. If the array is more than 60K byte, using the list it will get more data. Even though the total limit for the LS is 256 KB, and since you are
Okay. So if I got single data which is more than 16K data transfer, then I can use list.
All right.
You can use DMS, regular DMS also, but it takes overhead in setting up a DMA every single time. Over here, you're saving that overhead.
Okay.
Maybe the total limit maybe for future things when they have in future processors they have more data size than LS, and so that restriction maybe they have scope for expansion of the LS size.
I had a different question in mind. Okay, basically a list does it in chunks. Okay, so even if the list is not over, I can actually start processing the first chunk.
Yes.
Is that the advantage?
Exactly. Got it. Because it's asynchronous.
Okay. But then there is no mechanism for me to know which chunk is finished.
And that's, we have to leave that up to the God. That's the compiler.
No, is there any way of knowing
Sorry?
that? Is there a way of knowing? Like, see, when I do a MFC get, I do check for the status.
Yeah.
It is over.
Yeah, that's up to the runtime environment to see, okay, is the data there? Then it will go ahead and process it. Because you have...
Inside the program, can I find out that what is the status? First list item is over, second is over, third is over. No.
As far as I know, there is no feature.
But there was a tag bit, no?
Yeah, you can wait for the completion of the DMA, but you can't go and check on
Each list element has got a tag bit.
No, they all have one tag bit.
Each list element had a tag bit.
Sorry?
Each list element, your 8-byte element has got a tag bit.
Same tag bit. It's all under one category.
Oh,
The whole list.
so I thought that was used for completion or non-completion.
No, it's for one whole list has one tag bit.
One at a time.
For DMA list is you can transfer the whole chunk together, but then double working is much better. You can start processing the you don't have to wait for the full data to release.
Okay, this is an example of double buffering on the PPU program. PPU program the same, nothing changed, right? Straightforward, and then initialize array. The programmer here is the SPU, and okay, the check for the working hardware, and then I do I identify the buffer here. Okay, I have the array size times I divided by 8. It's the offset into my array, and then so this is the 64, the first 64 byte here. For the offset sub I, increase at 1, and then start array in the cache line. Get the control blocks, going down. Okay, let me do this. Let me go and get the SPU program. SPU is better.
They're asking a tea break.
Tea breaks.
I'm not sure.
5 minutes tea break. 5 minutes, and then I take an offline some questions. Okay, come. Yeah. Okay, let me bring up the SPU program as well.